Okay, so then we can start. So good evening, everyone, and welcome to the second session of this problem solving series for this course Advanced Power Electronics and Control by Professor Ravi Bhattacharya from IIT Roorkee. So I am Nandh Kishore from the Department of Electrical Engineering, IIT Delhi. So I am a PhD student in the E department under the supervision of Professors Soumeshwar Pranag and Sumit Pramanik. Okay, so in your course in the last week, these topics were covered. The leftover electronic switches from the last week, that is IGCTs, MCT, and then SITH, MOSFETs, and IGBTs were covered. That is the device physics were covered. And then you also had some discussions about the switch specifications, that is what are the characteristics of an ideal switch and how do you select devices for different applications. And you also had a brief discussion on gate drive circuits. So that is gate drive for IGBTs, gate drive circuit for MOSFETs, and so on and so forth. Okay, so apart from these, up to this point, up to gate drive circuits, that actually marks the end of your electronic switches. After that, you started off with rectifier circuits, which are basically AC to DC conversion circuits. So you went through some basic terminologies associated with rectifier circuits, including what is form factor, what is ripple factor, what is total harmonic distortion, what is distortion factor, and so on and so forth. You had a number of terminologies, I guess. And then you started off with single phase rectifiers. In particular, you covered uncontrolled single phase rectifiers just using diodes, and then you came over to control single phase rectifiers that are implemented using ACRs, right? So I guess this is an overview of what was done or covered in the last week. So today we will be having a problem solving session. So since you had a mix of electronic switches and single phase rectifiers, so this problem solving session will have a mixture of questions from both topics. So towards the end, I also have a few numerical problems which could not be covered in the last session because last session was entirely theoretical, as you may be aware. So today I have a few numerical problems that we will solve in the end. So in the starting, I have a lot of theoretical problems. I think we can speed up and cover up those problems faster, and then we can devote more time for the numerical problems as well. Okay. So without further ado, we will go ahead. Okay. So this is just a summary of electronic switches that we generally use for power applications. You have your diode, which is totally uncontrolled and operates only in the second quadrant. That is, it can block reverse voltage and conducts only unidirectional current, as you can understand from the quadrant operation over here. And then you have the conventional BJTs, bipolar junction transistors, that can block forward voltage until it is supplied with a base current. And if it is supplied with a base current, then the BJT gets forward biased and it can carry unidirectional current. Right. And then you have your SCRs and GTOs. So the GTOs is GTO is an advanced form of SCR wherein you have control over its turn off as well. As you might remember, in SCR you have control over only its turn on. During turn off, it's uncontrolled. So that's why you call SCR and semi-controlled device. But GTO is an advancement of that, wherein you have control over the turn off as well. So you may be aware that in order to turn on an SCR, in order to make it forward bias, you need to apply a positive voltage. Also, you need to make sure that the gate current is more than the matching current, right? So similarly, in the sense that if you want to turn on the SCR, you need to supply a high or a high value of a positive gate current signal to turn on the SCR. For turn off of the SCR, that is not sufficient. You need to apply a sufficient reverse bias voltage, right? Only then the SCR can turn off. So you have a number of circuits which you may be coming up, you may be studying in later chapters as well, which are known as commutation circuits, wherein you will study how to turn off these SCRs. But GTO is an improved version of that, wherein you have the flexibility that you supply a sufficient enough negative gate current, and then the GTO or the device just turns off. And it has similar characteristic, similar to ACR. So it has unidirectional current capability and bidirectional voltage capabilities, right? And then you have the APTs or the MOSFETs. So you have bidirectional current capability thanks to the anti-parallel diode, which is connected between the source and the drain. And of course, it can block positive voltage because as long as your VGS, that is your gate source voltage, is less than the threshold voltage, the MOSFET does not turn on. So it can block positive voltage, it can conduct current in either direction, from drain to source or source to drain, right? Okay, having said all of this, ideally, we want to realize this, which the last one that's shown over here, that is voltage bidirectional and current bidirectional. It should be able to block bidirectional voltage, conduct current in both directions. So essentially having a conduction in all quadrants. So one switch that has been able to emulate that so far is the triac, right? Bidirectional triode thyristor, wherein you have two SCRs connected in anti-parallel, right? Okay, anyway, so this was just a recap of the devices. We will jump ahead to the questions. So at any point of time, if you have any doubts, you can go ahead and stop me and I will be happy to explain it to you again. Okay. So this is a pretty simple question. What is the full form of IGCT? So IGCT is basically integrated gate commutated thyristor, as you may be aware. So IGCT is an improved version of GTOs. So in the previous slide, I was explaining to you about GTOs, how GTOs are an advanced version of SCRs, right? So in SCRs, you have only turn on control, right? And in GTOs, you have control over its turn on as well as turn off, right? So in IGCTs, what you do is, okay, you have the GTOs, you have control over its turn on and turn off. So what further improvement we can have? So one thing is you can have an integrated gate, right? So what is the advantage of having an integrated gate, or what is integrated gate? So what happens is the structure of an IGCT is something like this. So over here, it may not be that clear to you, but anyway, over here, the gate is integrated into the device itself, right? So what happens is, for generally, if you take MOSFETs as an example, when you supply the gate pulses or the pulses from the microcontroller, that alone is not enough to drive the device. You need to have something called as a gate driver, right? You need to have something called as a gate driver, which will amplify the signal and provide you isolation and stuff, okay? A better version of that would be integrating all the circuitry or the gate drive circuitry into the device itself, okay? So this is what is called an IGCT, wherein inside the thyristor itself, you have an integrated gate. Okay, so it's an improved version of GTO. Essentially, you will have control over its turn on and turn off as well. And the idea is, since you're integrating all of them into a single package, the losses will be actually lesser. So a practical visualization can be something like, okay, so earlier you had all those discrete devices which you needed to connect individually, right? So, but if you take your CPUs or computers, you have integrated circuits or what are known as ICs, right? So in a single IC, you will be having a number of BJTs, number of MOSFETs that are realized in a monolithic fashion. Okay, so they are fabricated in such a manner. Okay, so that's an example. So what you achieve with that is you have a part and solution, or within a single device or within a small device, you are able to achieve so much functionality. Okay, so that's the that's the explanation for this. You have an integrated gate inside the thyristor. So that is what is called an IGCT. So because you're integrating everything together, the gate inductance, that is your gate inductance is essentially some parasitic. Okay, so gate inductance is lesser and your losses are lesser. Okay, so essentially it's an improved form of GTOs. Anyway, the correct answer for this question would be integrated gate commutated thyristor. Okay, so we will go ahead to the next question. RC IGCTs are known as dash. Okay. So you may be aware from the lecture slides as well, I think it was explained by the professor. So IGCTs are of two types. Okay. So the conventional IGCTs are they classified into two types known as symmetrical IGCTs and asymmetrical IGCTs. Okay. So what are these? So as I told, based on whether you have an antiparallel diode between the cathode to the anode, right? I call it antiparallel because it's connected between the cathode to the anode. If you see, let me turn on my laser pointer. If you see over here, there is an antiparallel diode that's connected between the cathode to the anode, right? So if you have this and if you don't have this, right? So based on that, you can have two types of IGCTs, that is symmetrical and asymmetrical IGCT. So as you can understand, this if you have an antiparallel diode, then it's called an asymmetrical IGCT. So you can understand that once you have an antiparallel diode, it cannot block reverse voltage, right? Because let's say I apply a voltage something like this, then this device cannot block the voltage or this reverse voltage. Why? Because once you apply this voltage, this diode gets forward biased and current will start flowing like this. Okay. So that is the reason in the quadrant operation as well, I have shown it is capable of bidirectional current conduction, right? Bidirectional current as in like it can conduct current from here to here, or it can also conduct through the diode from cathode to the anode, right? So anode to cathode and cathode to anode both are possible in this. Bidirectional current conduction is possible, right? And it cannot block voltage in the reverse direction. So it can only block voltage in the forward direction, right? So only this is possible. Okay. So as long as you don't supply this gate pulse to this thyristor or to this IGCT will not turn on. So it can block positive voltage. It cannot block negative voltage, but it can conduct current in both directions. That is from anode to cathode and cathode to anode. Okay. So this is an asymmetrical IGCT. So you can understand that asymmetrical IGCT cannot block reverse voltage, right? Whereas symmetrical IGCT, asymmetrical IGCT is just the IGCT alone. You don't add any extra antiparallel diode. So by the way, this antiparallel diode can be added externally or through fabrication processes. You can also create an antiparallel diode inside. But anyway, so over here, this is called a symmetrical IGCT, just the IGCT alone. You don't have an antiparallel diode. So as you can understand, this is similar to like, this is similar to ACRs, right? So wherein bidirectional voltage blocking is possible and unidirectional current conduction from anode to cathode is possible. Okay. So if I supply gate current over here, then this IGCT will get forward biased and it will conduct current from anode to cathode. If I don't supply gate current, then it can of course block voltage in the positive direction as well as it will block voltage in the negative direction, but it cannot conduct reverse current, right? So anyway, the question was RC IGCTs are dash, right? So RC IGCTs are asymmetrical IGCTs that are fabricated with a reverse conducting diode in the same package, okay? So in the same package, they are fabricated with a reverse conduction diode, okay? So RC IGCT is a reverse conducting IGCT as indicated over here, okay? Okay, so we'll move on to the next question. In the case of high voltage applications, we use dash. And in the case of high frequency applications, we prefer dash. Okay. Okay, so this should be pretty simple enough for you guys to answer. So for high voltage applications, we prefer IGBTs. And for high frequency applications, we prefer MOSFETs. Why? The reason is that IGBTs, the reason lies in what kind of devices they are. Okay. So IGBTs, as you may be well aware, they are minority carrier devices, whereas MOSFETs are majority carrier devices. So any majority carrier device, can turn on and turn off fast. Okay. So a majority carrier device guarantees faster switching. That is faster switching as in like T on and T off is actually very low. It can turn off faster, turn on faster, which means that if I can turn on faster and turn off faster, I can use it for higher frequency applications, high frequency applications. Okay. On the other hand, On the contrary, IGBT is a minority carrier device. Okay, so minority carrier device, as you may be aware, they have something called as a reverse recovery during turn off. Okay, and they also have property known as conductivity modulation during turn on as well. So these, because of these features, that is due to reverse recovery, essentially, the turn off time is pretty large, which means that since your turn off time itself is very high, you cannot directly use it for high frequency applications. However, because of this particular property, conductivity modulation, you can actually use it for very high voltage applications or high power applications. Okay, the reason is because of conductivity modulation in minority carrier devices, the turn on, the losses in the on state are actually very low compared to MOSFETs. Okay, why? The reason is, that, let me explain over here. Okay. The reason is for majority carrier devices and minority carrier devices. Okay, so when they are completely turned on, that is when they are completely forward biased. So if you can remember the VA characteristics of a MOSFET, right? So it will be something like this, right? So what happens is this particular region. So this particular region is known as ohmic region, right? And after this, the current has saturated, right? So this region is called saturation region. Okay. So when the MOSFET is completely turned on, the device actually operates in the ohmic region. Okay. So when it operates in the ohmic region, it has a constant slope. Okay. This slope is actually constant, which means that I will have, if I take this slope, so this is actually VDS and this is IDS. Okay. From MOSFETs, drain to source voltage and drain to source current. Okay. So this slope will be delta ID is divided by delta VD is, that is equal to 1 by R on. So this is the on resistance of the MOSFET. Okay. So as you can understand, when the MOSFET is turned on, the loss across the MOSFET will be turn on loss, or the P loss when the MOSFET is completely turned on. The loss will be IDS square R on, right? So this will be the last loss that is incurred across the MOSFET. So as you can understand, as you go for high power applications, this IDS will be pretty large. Okay, so this IDS is also large, and you are taking a square of that, and then you are multiplying with R on. Okay, so it's a pretty large I square R loss that occurs across the MOSFET as you go for high voltage, high power applications. On the contrary, for minority carrier devices, you have a similar VA curve, correct? So you have a similar curve. For example, if I take IGBTs, that is collector to emitter voltage, and you have the collector current, right? So you will be having characteristics something like this. Okay, of course. We'll be having something like this. Okay. Okay. So what happens is the loss across the IGBT, right? When the IGBT is turned on, so you have your IGBTs. This is your collector, emitter, and then your gate. So when you apply a positive VGE over here, then there will be a constant drop VCE that occurs. Okay. So irrespective of the voltage of operation, right? Irrespective of the power, or irrespective of the current level over here, IC over here, there will be a fixed drop that occurs across the BJT or across IGBTs, which means that your loss over here, when it is completely turned on, is going to be VCE times IC. Okay, this VCE is constant. This VCE depends on where you're operating in this VI curve. So it can be here, 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 or whatever. It depends on your current rating and then your voltage rating. So it can be here or wherever it can be. However, the loss across the IGBT will be fixed. That is VCE times IC. So you have your IC and then you just multiply with a fixed drop that occurs across the collector and the emitter. Okay. So as you can understand, you have a square term over here that's getting multiplied with your channel resistance. Correct? In majority carrier devices like MOSFETs. Majority carrier devices like MOSFETs. However, in minority carrier devices like diodes or IGBTs, what happens is you have a fixed loss, that is VCE. I mean, this drop is actually fixed. So VCE times IC. Okay, so that's why we generally use IGBTs for very high voltage applications. However, MOSFETs have a loss that's proportional to your power level. As your power level increases, your loss also increases, right? Too much because it's I square times R on. So because of that, we use MOSFETs for high frequency applications. So IGBTs, you operate only till, let's say around 10 kilohertz is the maximum you can operate. Okay, 10 kilohertz are max maybe 20 kilohertz, not more than that. Generally, you have applications that are 5 kilohertz, 10 kilohertz and stuff like that. So generally for variable frequency drives that you may be aware. So they are for 5 kilohertz and 10 kilohertz. However, MOSFETs can be used for very high frequency applications such as 100 kilohertz, 250 kilohertz. With advancements in the device manufacturing and device technologies, people have gone towards megahertz. People have gone toward megahertz applications as well, like 7 megahertz, 1 megahertz, 6.78 megahertz and stuff. Okay. So essentially, this is the reason why majority carrier devices are not used for high power and high voltage applications, whereas minority carrier devices are used for that. However, majority carrier devices provide a very fast turn on and turn off. As I was telling you, minority carrier devices have something called as reverse recovery, right? So they have a reverse recovery, which means that your turn off time is very large. Okay. For MOSFETs, however, your turn on and turn off times are very low. Okay, because of that, you can actually go ahead and use MOSFETs for high frequency applications. High frequency applications. Okay, so for IGBTs, you cannot, of course, use them for high frequency applications. So the answer is, in the case of high voltage applications, we use IGBTs, and for high frequency applications, we use MOSFETs. Okay. So the trick over here was just that you needed to identify whether, which of these is minority carrier device and which of these is majority carrier device. Then you can, of course, apply your logic and give the correct answer. Okay. So the next question, this is pretty simple. Which of the following characteristics are ideal, are for an ideal switch? On resistance is 0 and off resistance is infinite and so on and so forth. Okay. So what is your ideal switch? As we discussed in the starting as well, an ideal switch should be able to block bidirectional voltage, and it should be able to conduct bidirectional current. That is, it should be able to conduct from anode to cathode and cathode to anode, and of course block voltage, that is forward voltage or reverse voltage, whatever, right? Ideally, you want to emulate a 4-quadrant switch. So that is your ideal switch. Nonetheless, when it is turned on, you want the switch to operate as a complete short circuit, right? You don't want any drop occurring across it, such as the VCE drop that we were seeing earlier. You don't want that drop, or you don't want the RDS on, that is the channel resistance, to come, as in the case of MOSFETs, right? So ideally, you want your on voltage drop to be 0, and you want it to block infinite voltage and not allow any current, any leakage current when it is turned off, right? So that is what you ideally want. So for example, as I was mentioning earlier, when the device is turned on, in case of a MOSFET, you have something called as RDS on, right? So in case of a MOSFET, you have okay, so when it is completely turned on, you can actually approximate the entire channel as an RDS on. Okay, drain to source resistance. So as I told you, when a current IDS flows over here, there will be a loss IDS square RDS, right? Similarly, for an IGBT as well, you have you have an IC collector current, and but you will have a fixed drop across this between the collector to emitter, right? So the loss will be something like PCE times IC. Okay. However, ideally, you want this VCE to be zero, or you want this RDS to be zero, right? So that is the characteristic of an ideal switch. So that is why the on resistance needs to be zero, right? On resistance needs to be zero, RDS needs to be zero, and off resistance needs to be infinite. So when the switch is turned off, so when the switch is turned off, or if your gate source voltage is less than threshold voltage, you want the device to completely block the voltage, right? You don't want it to conduct any current when the device is turned off, right? So that's why you want your off resistance to be infinite. So the answer for an ideal switch is, I mean, this on resistance is zero and off resistance is of course infinite. Okay. So this is pretty simple. How to turn off the GTO? So by applying a high negative current at the gate, by applying a antiparallel diode with the device, by applying a freewheeling diode, and none of these. Okay. So as I was mentioning earlier, SCR, you can have control only over its turn on, right? Turn off is not controlled, therefore SCR, that's why SCR was called a semi-controlled device, right? So GTO is the next version of SCR, right? So GTO is a fully controlled device wherein you have control over only over both its turn on as well as turn off, right? So during turn on, what you do in SCR, you apply a high or a positive gate current, right? You apply a positive gate current pulse and then the ACR turns on. However, the turn off is not simple, right? You need to apply a sufficient reverse bias voltage and then make sure that the gate current is, the current is less than the holding current of the device and stuff, right? For GTOs, it's an improvement of ACR in the sense that while turning it off, you can apply a sufficient negative current. You apply a sufficient negative current and then the GTO just turns off. Okay. Turn on is similar to ACR and turn off. It's just a complement of what you do during turn on. You apply a high negative current at the gate and then the GTO turns off. Okay. Okay, so the switching times of a MOSFET essentially depends on what? Frequency, the charging and discharging rate of parasitic capacitors, the charging and discharging rate of parasitic inductors, power, voltage, current of the given system or what. Okay, so this is actually the typical structure of a MOSFET. So what you may be aware as a MOSFET structure may be something like this. So you have a drain, a gate, and then a source, right? So, and of course you have the anti-parallel diode. Okay. So this is what you may be aware of as the typical structure of a MOSFET. However, you should understand that inside the device package, what is formed is a parasitic capacitances, a parasitic capacitance, right, between the gate and source. So this is called a CGS. Okay. Similarly, between the source and the drain, I mean the gate and the drain, you have something called a CGD. Okay. And then between the drain and the source, you have something called a CDS. So if you go into the dynamics of how a MOSFET turns on and how a MOSFET turns off, it is basically the discharging and charging of these capacitors over here, right? So, for example, you tell that, okay, if your VGS is more than V threshold, then the MOSFET turns on, right? And if VGS is less than V threshold, then the MOSFET turns off. essentially what you're telling is if VGS is more than V threshold means the point is if the voltage across this capacitor between voltage of this capacitor CGS, if the voltage of CGS is more than V threshold, then the channel conducts. Okay. And if the voltage of the CGS capacitor is less than V threshold, then the channel does not conduct. Okay. So essentially, these capacitors completely govern the dynamics of how the MOSFET turns on and how the MOSFET turns off. Okay. So for example, I'll just take an example circuitry and tell you how the MOSFET actually turns on. Okay. So you will have something called as a gate resistance that's connected over here. Okay. And then you will have your pulses which are connected to the source. So I will call this as RG. Okay. And I will call this as VG. The voltage across this capacitor is VGS. Okay. So this is your pulse. So this is how you will be getting pulses, right? So as you can understand, let's say you apply a pulse over here, VG. Okay. Then let me call this as IG. If you apply a simple KVL in this gate loop, you get VG minus IG RG. Then you have minus VGS, that is the voltage across this capacitor, and then back to zero, right? So you can understand that VGS is essentially VG minus IG RG. Okay. And what is this gate current? You can understand that IG is essentially, so IG is essentially flowing over here, right? So this is the part of this IG. So the capacitor current is given by CGS into, of course, you have two paths for this gate current over here. So it comes to this point, it can flow through CGS, it can also flow through CGD. Okay. So if we consider just this voltage over here, so CGS into dVGS over dt, right? Plus CGD into dVGD over dt. Okay. So IG is basically what? IG is getting split into two branches, that is through CGD and through CGS. Okay. CGS into dVGS by dt plus CGD into dVGD by dt. So you can understand that this gate current is dependent on how fast you change this VGS, right? So IG is dependent on dVGS by dt. And where is this VGS going to or appearing across? This is appearing across this CGS capacitor, right? And of course, you have the CGD capacitor. So as far as that question was concerned, the turn on and turn off, the switching times of a MOSFET or the turn on and turn off times of a MOSFET essentially depends on how fast the CGS and CGD are getting charged and discharged. Okay. So allow me to just go a little deep into this concept. If you have any doubts, you can, of course, stop me in the middle and I'll be happy to explain. Okay. Okay, so we have this one equation over here. IG is a summation of the capacitor currents. You can also apply KVL in this loop. Okay. So let me call this as VGS. Okay. This is VDS. Okay. And this is VGD. If you apply KVL over here, you get VGS is equal to VGD plus VDS, right? Therefore, your VGD can be written as VGS minus VDS. Okay. So this is your second equation. You substitute VGD over here. So your IG becomes CGS into dVGS over dt plus plus CGD into d over dt of VGS minus VGD, right? So you can take CGD common. So CGS plus CGD into dVGS over dt plus CGD into d, sorry, VGS minus VDS. So VDS over dt. Okay. So CGS plus CGD into dVGS over dt plus CGD into dVDS over dt is your gate current IG. Okay. So I will call these two capacitors CGS plus CGD as CISS. That is the input capacitor. Okay. Input capacitor to the MOSFET. So dVGS over dt plus CGD into dVDS over dt. Okay. So this is your IG. Got till this point? IG is CISS into dVGS by dt plus CGD into dVDS by dt. So till this point, is it fine? If you have any doubts, you can stop me. Okay, I'll just pause for 2 minutes over here. You just try to understand what we have done. So what I did was I just connected a voltage source over here, and then I have a gate resistance called as RG, and then we have these two capacitors CGS and CGD. Okay, I just applied KCL over here at this node. So IG is equal to CGS into dVGS by dt plus CGD into dVGD by dt. Okay, this was one equation. And next we had VGS as a summation of VGD and VDS by KVL, simple KVL, right? So VGS is equal to VGD plus VDS. Okay. So I just rearranged the terms over here. VGD, I wrote it as a summation of VGS and VDS. Okay, so then I ended up with this equation. IG is CISS into dVGS by dt plus CGD into dVDS by dt. Got till this point? Can anyone please answer me? Like, if it's fine. So can anyone answer please if that was fine? Till this point?
Yes, fine till this point, sir.
Okay. Okay.
It should be minus CGT.
Oh, sorry. Okay. Thanks for pointing out. It is minus. Thank you. So CISS into dVGS by dt minus CGD into dVDS by dt. Okay. You can have this as equation number 3. So I will add a new slide over here. Oh. Now we will go back to the original KVL equation. So we had VG is equal to or VGS is equal to IGRG plus VG, right? So this is what we had. VG plus IGRG is your VGS, right? You can see this loop over here. VGS across this capacitor, VGS is equal to what? VG minus IGRG, okay? VGS is VG minus IGRG. So what you can do is you can go ahead and substitute that equation of IG, that is CISS into dVGS over dt minus CGD into dVDS over dt into RG. Okay. So this is your VGS. I will call this as equation 4. Okay. So now you see that this VGS, of course, it's a function of time. VGS of t is equal to VG. This is some fixed voltage, VG, minus CISS, right? So CISS is your input capacitance, as I called it. It's a summation of CGS plus CGD. Okay. So CGS plus CGD, okay, into dVGS of T over dt minus CGD into dVDS of T over dt into RG. So you can understand that how this VGS changes. It is a function of these capacitances CISS and CGD, and it is also a function of RG, right? Gate resistance. Okay. Basically, if you solve this, it's actually an ordinary differential equation. So if you solve this, it will be just like a RC charging. The equivalent circuit is something like this. So you have your a supply over here Vn, and you have your output over here, and you have an RG, and I'm calling this as CISS. Okay. So you will see that, okay, so essentially your V naught is going to be equal to Vn, just that the dynamic or how it is changing or how it is getting charged up depends on this RG value and the CISS value. Okay, got it. So this has a direct bearing on the MOSFET channel current, because you know that when the channel current of a MOSFET is channel current of a MOSFET is given by each channel is GM times VGS minus V threshold, right? You may be aware of this equation, right? So this VGS is actually this. Okay. How this VGS changes or how this VGS charges up directly affects your channel current. So you can understand how the channel forms in the MOSFET depends on how your VGS is going to charge. Okay. Or how your CGS or your capacitors are going to charge up. And how VGS changes, as I told, depends on the value of these capacitances and of course your gate resistance. Okay. Got it. So this is an idea of how a MOSFET actually charges and how the MOSFET capacitance is charged and how the MOSFET turns on and how the channel forms. Okay. So essentially for this question, the switching times depends on the charging and discharging of these capacitors. So I just took the example of MOSFET turn on alone. Similarly, you can have the same for MOSFET turn off, just that the currents will be in the opposite direction. During turn off, the capacitor will discharge. Okay, right? When the capacitor charges up, you understand that the current is like this. When the capacitor discharges, the current will be like this. You are taking out current from the MOSFET capacitance. Okay, so the current will be like this. Okay, so similar equations can be formulated for turn off as well, just that the current IG current will be reversed. Okay. So I think it is pretty clear, right, for you guys, like how the MOSFET turns on and what is the bearing of the capacitance and the RG values on how the MOSFET charges it. Okay, so that was about the devices. Now we will come to a next question, right? So what's that time? Okay. So which of the following relations is true? If form factor is this much, then what is the ripple factor? So you just need to, this is from a question from the device terminologies. Okay. So, so you may be well aware that form factor is RMS value by average value. And your ripple factor is root over RMS square minus average square divided by average. Okay. So you rearrange this, you will end up with ripple factor is root over form factor square minus 1. Okay. So ripple factor is root over form factor square minus 1. Just you need to know the definition of form factor and ripple factor. Form factor is RMS by average. Ripple factor is root over RMS square minus average square divided by average. Okay. So you just rearrange this. You will end up with ripple factor is equal to root over form factor square minus 1. Okay. So you can just check which of the options matches for us. So ripple factor is root over form factor square minus 1. So first option is if form factor is root 5, ripple factor is 2. So root 5 square is 5 minus 1. is 4. So root 4 is 2. So this answer matches. Okay. Form factor is root by ripple factor is 2. Okay. Ripple factor is root of form factor square minus 1. That's the key. Okay. In a certain power electronics application, it is required that the voltage at the load terminals is to be kept within a certain range of voltages only. Among the devices listed below, which would be the most ideal choice for this application? PN junction diode, Schottky diode, Zener diode, and fast recovery diode. Okay. So the idea is, the question is, you want to maintain a particular voltage. Okay. What device would you use? So PN junction diode. Of course, you may tell that, okay, when the PN junction diode is forward bias, the voltage drop across this will be around 0.7 volts. But it is only 0.7 volts. It's not something controllable, right? Across all power diodes, this is something you see between 0.7 to 1 volt. Okay. It cannot, of course, give this much. It cannot, of course, have variable voltage ranges. You buy any power diode, they will have a fixed voltage drop across them, right? And the voltage drop will be fixed irrespective of their voltage rating and current rating. The voltage will be anywhere between 0.7 volts to 1 volt. Okay. So this is not the answer. Schottky diode is just an improvement of normal PN diode, just that instead of a P over here, you have a metal contact. Okay. So again, Schottky diode is not the answer. Of course, they will have a larger drop. Generally, Schottky diodes tend to have a larger drop. However, they are not the answer. Fast recovery diodes are just an improvement of PN diodes because basically the reverse recovery time is lesser. So the answer for this is Zener diode. So as you may be aware, in a Zener diode, you always operate it in the third quadrant, right? So this is your third quadrant. So what happens is there is something called a phenomenon called Zener breakdown that occurs. So at this particular operating point, you have a pretty straight value of current over here, okay, around a 90-degree slope, which means that the device continues to operate at a particular voltage and the current is almost fixed. Okay. So when that Zener diode is reversed bias, what happens is something called as a Zener breakdown occurs. That is, a large, high concentration of charges will appear at this operating point. So the reverse voltage remains constant, whereas the current increases. So that is why when you always connect your Zener diode, you always connect something like this. So let's say across this you want to maintain, let's say 6.3 volts. You will connect your 6.3 volt Zener something like this, anode and cathode. So you will connect it in reverse, right? Anode will be over here and cathode will be over here. Uh, okay, this is how you will connect it. So essentially, answer is Zener diode. So Zener diode can maintain a particular voltage. So in the market, multiple types of, multiple Zener diodes with different breakdown voltages are available. So based on the doping, this VZ can vary. It can be here, 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 or anywhere. Okay. So if you want 6.3 volt Zener, they are available. 5.7 volt Zener are available. Zeners are available, and so on and so forth. Okay, at different breakdown voltages, you get different packages of Zener diodes. Okay. So for the power semiconductor devices, IGBT, MOSFET, diode, and thyristor, which of the following statements is true? All the four are majority carriers. Okay, so we will first. So there's a question on majority or minority carriers. So we'll just label them. IGBT. Right? So IGBT, as you may be well aware, it is actually a MOSFET driving a BJT. Okay. So that is why you have an insulated gate and then you have a BJT kind of a structure for a IGBT, right? So you apply a VGE and you control your IC. So the point is that you have a BJT which is conducting the power current, right? So IGBT is a minority carrier device. So MOSFET, as you may be well aware, is a majority carrier. Okay. Diode is again a minority carrier, right? And thyristor is again a minority carrier, right? So essentially the answer is this. MOSFET is a majority carrier device. IGBT, diodes, and thyristors are minority carrier devices. Okay. Which of the following devices does not belong to the transistor family? GTO, IGBT, MOSFET, and BJT. Okay. So I think you know the answer is GTO because this is gate turn off thyristor. Okay. IGBT is insulated gate bipolar transistor. MOSFET is metal oxide semiconductor field effect transistor. And again, you have BJTs as bipolar junction transistors. So GTO is a thyristor. It does not belong to the transistor family. Okay. Okay. So the next question is VFDs. So some of you may not have learned about VFDs. Anyway, this question is not too deep into that. VFD. So what are variable frequency drives? So as you can understand from the terminology itself, it is a drive, right? So anything, so anywhere you see a name drive, it means that it has something to do with motor torque control or motor speed control. Okay. So you understand that variable frequency drive means a torque is getting controlled and the speed is getting control of what? A motor. Okay. So that is one. Second thing is you have something called a variable frequency from the name itself. That means that you are varying the frequency. Frequency is getting varied in order to control your motor torque and motor speed. So from the options, I think you can guess that you control the motor's input frequency and the voltage by varying motor speed and torque. I am sorry, you control the sorry. You control the motor speed and torque by varying the motor input frequency and voltage. Okay, so you are controlling the motor torque and motor speed by controlling the motor input frequency and voltage. So how? Any AC machine operates on the principle of flux balance. Okay, essentially the net flux should be constant. Okay, or the net flux should be zero. That is the idea, right? In any AC machine, the net flux should be zero. Okay, the average flux or the net flux should be zero. So you may know from Faraday's law of electromagnetic induction that the induced EMF is N times d phi over dt, right? Right. So E is N times d phi over dt. So from just the units alone, you can write that, okay, this is N times phi by t. Okay, this is proportional to N times phi by t. So N times phi times. So 1 by t is essentially frequency, right? 1 by t is frequency. So N times phi times frequency. Therefore, you can tell that phi is proportional to E by F, right? So N is anyway a constant, right? So if I take F over here, phi is proportional to E by F. So I will change, E is this EMF or voltage, okay? So I will change my voltage and change my frequency such that phi is constant. Okay, that is what we do in variable frequency drives. For those of you who are not aware, you will eventually learn it in your other courses, maybe in your drives course or machines course. But anyway, in VFDs, as I told, you control your EMF, you control your frequency, you vary your frequency and voltage so that you are able to control your AC motor speed and your torque. Okay, so this is the right answer for this. Okay. When a physical contact between a P region and N region is established, which of the following is most likely to take place? Okay, so let's say you have something like this. So a P region and a N region. Okay, so as you are aware, N region is full of electrons and P region is full of holes or positive ions, right? So when you connect both of them, what will happen? opposite charges will attract. So P holes will cross over from the P region to your N region, and electrons will cross over from here to here, right? So electrons will diffuse from N region to P region. Holes will diffuse from P region to N region. Therefore, both of these will happen, right? So both of these will happen, and eventually what happens is a depletion layer gets formed, right? So the nearby, this over here will get diffused with this, these holes will get diffused with this, and eventually a region of neutral ions will be formed. So you have your P over here and your N over here, and then you have something called as a depletion region, right? So you have your anyway, but when you connect, when a physical contact occurs, then what will happen is essentially these two electrons will go from here to here, and holes from go from here to here, right? Okay. High frequency operation of any device is limited by forward voltage rating, switching loss, thermal conductivity, and heat sink arrangement. Okay. So what happens when you turn on and turn off? So as I was explaining earlier, I was explaining the MOSFET turn on and turn off, right? Anyway, so what happens is, so ideally, let's say during turn on, right? So what happens during turn on? The current goes from I equal to 0 to whatever is the load current I naught, and the voltage across the device, right? Voltage will fall from whatever forward voltage it was blocking to 0. So essentially, you will be seeing that ideally what you want is your VD or the device voltage will fall from V naught to 0, and your device current you want it to increase from 0 to I naught. So this is what will happen during turn on. Okay. So this is during turn on. Okay. Similarly, during turn off, what is supposed to happen? Your current will fall from I naught to 0, and your voltage will increase from 0 to V naught, forward voltage. Okay. So this is during turn off. So this is something very ideal. Okay. So this is the ideal case. Okay. However, practically, if you see, so I'll just take a new slide. Okay. So practically, if you see what happens is during turn on, the current will not increase immediately from 0 to I naught. It will increase slowly from 0 to I naught. Okay. It will have a specific rise time. Similarly, so this is your ID. Okay. Similarly, your device voltage will not fall instantaneously from V naught to 0. It will fall slowly. It will fall very slowly from V naught to 0. Okay. So this is your V naught. So this time interval, this is called your turn on time. Got it? So this is your turn on time. Similarly, during turn off, what you will see is your current will fall slowly from I naught to 0. And of course, there may be reverse recovery as well. Okay. And your voltage will increase slowly from 0 to V naught. Okay. So this I will call as turn off time. So ideally your turn on and turn off times will be 0, right? However, practically in a practical switch, you will see some turn on and some T on and some T off. This can be of the order of a few tens of nanoseconds to hundreds of nanoseconds, even microseconds to a few tens of microseconds, depending on the device. So for IGBTs, you will see something like this. And this is for MOSFETs. Okay. For MOSFETs, you will see turn on times of the order of tens or hundreds of nanoseconds, or for IGBTs, you will see of the order of a few microseconds. Okay. And as I was explaining earlier, the reason is because MOSFETs are majority carrier devices, they can turn on and turn off faster. IGBTs are minority carrier devices, you have something called as a tail current, which means that because of minority carrier devices, they need to, there is a process, there is a process, I mean, it's called a recombination. Okay, because of recombination of the charge carriers, minority charge carriers, it takes longer to turn on and turn off. Okay, anyway, so we have definite turn on and turn off times over here. Okay, because of this, every time you turn on the device and every time you turn off the device, there will be T on and there will be T off. Okay, so you see that during this T on, you see that voltage is also non-zero and the current is also non-zero, right? Voltage is increasing and the current is decreasing. So at a particular point, you see, that um, voltage is also non-zero and current is also non-zero. Okay, which means that there is going to be a loss during these periods. Okay, so we call this as P on. We call this as P off. Okay, and this will be proportional to V naught into I naught into T on. Okay, and this will be, okay, sorry, there will be some energy expended during this period. I will call this as E on, switching energy. Okay, we call this as switching energy, and this will be proportional to V naught, I naught, and T on. Similarly, the E off, switching energy. Okay, so switching energy during the turn off period is proportional to V naught I naught into T off. Okay. So this will be proportional to V naught into I naught into T off. So this is your switching energy. We call this as switching energy. So we call this as switching energy. That is, this much amount of energy is spent each time the device turns on. Each time the device turns off, this much amount of energy is spent. Okay. And the energy spent is directly proportional to your voltage level, your current level, and the time for which this period is persisting, time for which the turn on or turn off is there. Okay. So this is your switching energies. So from the switching energy, you can compute what is your power loss. Power loss is simply E on times frequency. Similarly, this is P off is simply or equal to E off times your frequency. Okay. So we understand that the P on the power, there is some power loss that occurs every time the device turns on and turns off. Okay. So as you go for higher and higher frequencies, you understand that this power loss is directly proportional to the frequency, right? So P is directly proportional to F. Okay. So every time you turn on and turn off, there is a loss. So higher the frequency, higher will be the loss, right? So as you go for higher and higher switching frequencies, you turn on and turn off the device that many number of times, right? You turn on and turn off the device. Like if you tell the switching frequency is 100 kilohertz, it means that you are turning on and turning off the device these many number of times, like right, 100,000 times for 1 second. Okay. So there will be a power loss every time you turn on and turn off, and higher the frequency, higher will be the power loss. Okay, got it? So just a summary of this question is, every time the device turns on and turns off, there is a power loss. Ideally, it should be zero, but practically it is not zero. Why? Because practically T on and T off, they are not zero. They can be of the order of a few hundreds of nanoseconds to a few microseconds as well, depending on the device. So there is a switching energy every time the device turns on and turns off. So the switching energy is proportional to V naught, I naught into this time period T on. and or switching energy during off period is V naught into I naught into T off, right? So this is the switching energy. This will be in joules, right? You generally express it in joules. And then if you want to find out the power, actual power loss, energy times frequency is your power loss, right? So as your frequency increases, the switch loss also increases. This is actually a loss, P loss. So this P loss also increases as your frequency increases. Okay. So the answer for this question is high frequency operation of any device is limited by switching loss. Okay. So there is a switching loss that occurs every time the device turns on and turns off. Okay. And as you go for higher frequencies, the loss also increases proportionally. Okay. Okay. So which of the following is true in the case of a forward bias PN junction diode? Okay. So you have your P junction, N junction, plus and minus.
Hello?
Yeah, yeah.
Yes, sir. Like, can you explain, like, for wide bandgap devices, how these switching losses will be less despite having high operating frequency?
Yeah, true. A good question. So the trick lies over here, T on and T off. Okay. So the point is for wide bandgap devices, let me just go to a new slide. Okay. So I'll just summarize over here. We saw that we had something called E on, which was proportional to V naught, I naught into T on, right? And we had something called as E off, which was proportional to V naught, I naught into T off. So essentially, your switching energy loss, total switching energy loss is E on plus E off, right? So every time a device turns on, it anyway has to turn off. So your switching losses are a summation of this plus this on and off, right? So V naught into I naught into T on plus T off. This is your E switching. Therefore, your switching loss, switching power loss that you see over here will be V naught I naught into T on plus T off into frequency, switching frequency, right? So the idea is, in let's say for IGBTs, the problem is your T on plus T off is really high. Your T on and T off are really high. That is why you cannot operate your IGBTs beyond a few kilohertz. You operate IGBTs at 5 kilohertz or 10 kilohertz maximum. Okay, because if you go beyond that, your T on plus T off into F becomes really high. Okay, and added to it, you always operate IGBTs for high power applications, which means that your V naught and I naught are also higher, right? So your switching losses will be really high if you operate at very high frequencies. That is why we limit your operation to 5 kilohertz. Now, the good thing with wide bandgap devices. So, for those of you who don't know, generally you may be aware that semiconductors are made up of silicon, right? So, semiconductors are essentially silicon. With advancements in the material technology, we have got devices made up of silicon carbide and gallium nitride. Okay, I've got devices made up of silicon carbide and gallium nitride. Personally, I am actually working on gallium nitride devices for my PhD, but anyway. So you have silicon carbide and gallium nitride that can turn on in the order of tens of nanoseconds. Okay, gallium nitride devices, they have been shown to turn on even within a few nanoseconds. Okay, less than 10 nanoseconds. Okay, so the idea is the T on and T off is very small. Okay, of the order of nanoseconds, which means that I can increase my F over here so that my P switch, so that I can also maintain the switching energy, switching losses within a particular value, right? At the same time, I'm switching the devices very fast. Okay, I'm switching the devices very fast. Your frequency is really high. The good thing with the devices is your T on and T off are also very, very low compared to silicon devices. For example, if I have to give an exact number, silicon turns on in 500 nanosecond to 1 microsecond. Okay, your SiC can turn on anywhere between 50 nanoseconds to maybe 150 nanoseconds max, right? Your gallium nitride can turn on between 5 nanoseconds to anyway, it depends on RG value. It can, let's say, 100 nanoseconds. Okay, this is very large actually, maybe 20 nanoseconds or 30 nanoseconds, something like that. So you see that from 500 nanoseconds, we have come to 50 nanoseconds, 5 nanoseconds and stuff. That means that 10 times reduction, right? And over here you have a 100-time reduction, right? So the T on and T off are going to reduce by 100 times, which means that I can increase my frequency by that much amount of time in order to get the same switching energy. Got it? So that is why WBG devices are generally operated at really, really high frequencies, very high frequencies. The reason is we get a cushion over here with SiC and gallium nitride devices that the turn on and turn off times are really low. Okay, so I can go ahead and increase my frequency. I can push my frequency to higher values. Got it?
Yes, sir.
In my own lab, we have people operating gallium nitride devices in megahertz range, right? So 6.78 megahertz and stuff. Okay, so yeah. And I'm operating it at 100 kilohertz. People operate it at 100 kilohertz and stuff. Okay. Okay. So, which of the following is true in the case of a forward bias PN junction? So, uh, positive P has this and this. So, as you can understand, the positive terminal of the battery sucks electrons from the P region, correct? So, it will try to attract electrons. And over here, this negative terminal will try to attract holes. So, this is the answer. The positive terminal sucks electrons. So I will try to speed it up from here because I have a set of numerical problems to be solved in the end. So I want to devote more time to that. I think this is pretty simple, right? Like PN junction diode, you just connect it across a battery. Then what happens? This is just like poles repel and unlike poles attract. So that's the basic principle over here. So choose a correct statement. Transistor will remain on as long as the base current is applied. True. Transistor remains on after a high to low pulse is applied at the base. Okay, so from the terminology, you can understand that this is about BJTs, right? You have a base over here. So what happens in BJTs? So you have IB, you have an IC, and you have an IE. You know very well that IC is equal to beta times IB. So your IC will flow only if IB is there, right? So you need a continuous IB in order to make sure that you can flow a continuous IC, right? So a transistor will remain on as long as the base current is applied. Okay. Okay. So even after the forward current reduces to zero value, a practical diode continues to conduct in the reverse direction for a while. Why? The reason is reverse recovery, right? So even if the forward current has reduced to zero, it continues to conduct in the reverse direction because of reverse recovery, right? So you call this as IRR, that is a reverse recovery current. And this time period is known as TRR, reverse recovery period. Okay. So the reason for this reverse recovery is due to stored charges in the depletion region. Okay. So the answer is this, due to stored charges. So recombination of the stored charges is the reason. Okay. For reverse recovery. Okay. So when the PN junction diode is forward bias, width of the depletion region obviously decreases, right? So you have a PN diode. So P and then N, you have the depletion region. So when it gets forward biased, when you apply a forward voltage, depending on the magnitude of the voltage, the width of this region decreases. It may become something like this or even lesser. Okay. So essentially the width of the depletion region decreases when the p-n junction diode is forward biased. Okay. So application of firing angle, why? To control the turn on and turn off times of the SCR, right? So if you have something like this, you may have studied in single phase rectifiers. So for a firing angle of, let's say, 30 degrees, the device will start conducting from 30. Okay. In case of a full bridge rectifier, full bridge AC to DC converter, this is 30 degrees, and if this is 180, this will be 210. Correct? V naught, and this is Vn. This is omega T. Correct? So this is your 30. It will start tracking the sinusoidal pulses after 30 degrees. Okay. Okay. So if you have any doubts, you can stop me and ask at any point of time. I'm just going ahead a bit faster in order to have sufficient time for covering the numerical problems. Okay. For a PN junction diode, the peak inverse current and the reverse recovery are dependent on what? Okay. So reverse recovery depends on what is the question. So you know that it is something like this, correct? So this we call as IRR. Okay. So let's say this. Okay. So this is your IRR. So this current, right, and this PRR, what should they be dependent on? They will be dependent on the di by dt over here. Okay, because you know that IRR is essentially what? So IRR is essentially di by dt times PRR. Okay. So this is the equation, and of course you know that the stored charge QRR is IRR times what IRR times PRR, something like this, right? So anyway, and you of course, yeah. So your IRR is dependent on this di by dt. Okay. So when reverse breakdown occurs in a diode, what happens? Voltage increases and current is constant. Voltage increases, current also increases. Both are constant. Voltage is constant and current increases. So when reverse breakdown occurs, this is what happens, right? So this is V, this is I. So this is almost a straight line, okay? So this will be a particular value of voltage, reverse voltage, and the current just goes on increasing in the reverse direction. So your voltage remains constant and current increases drastically during a reverse breakdown. Okay. So far any questions you can ask, because after this we will step into numericals. Okay. Yeah. One more question. IGBT and BJT both possess what? So what are these IGBT and BJT? Both of these are minority carrier devices. Minority carrier devices. So as I told earlier, minority carrier devices, they have a fixed voltage drop across them. IB. So you have a fixed VCE over here, right? So IC. So the loss is actually what? On-state loss is actually VCE times IC. Irrespective of the point of operation, the on-state loss will be VCE times IC, and the drop is VCE times IC. Okay. So that is why they are used for very high voltage and high power applications. So the answer over here is they have a low on-state power loss, right? As I was mentioning earlier, MOSFET cannot be used for high voltage applications or high power applications. The reason being that you have RDS on over there, and the loss will be I square times RDS, right? In MOSFET. Therefore, for high voltage application, this is a square term, right? But however, in for IGBTs and BJTs or minority carrier devices, the on-state losses or the on-state drop is fixed, VCE times IC. Okay. So this is done. Yeah. So next we are going into numerical problems. So if you have any doubt till this point, you can go ahead and ask. I'll just pause for 2 minutes and then we can start numericals. So anything at all? Or shall we start numericals? So if you have calculators, please do take them out. I'll give you 2 minutes. So we have some 5, 6 problems over here and it will be interesting to solve. So if you have calculators, please take them out. Try to take. Okay, so we will start. So the first question is find the minimum gate pulse width required to turn on the ACR in the following circuit. So this is my IG, right? So what is the minimum value of IG that I need to give, right? I mean, what is the time for which IG needs to be given so that I can turn on the ACR? That's the question. And I have given the value of the latching current and the holding current. IH is holding current and IH is a latching current. You may be aware, right? In an ACR characteristic, you have something like this, right? So you have your IL over here. I mean, you can have multiple something like this. Anyway, so during turn on, one thing is you look only at latching current during turn on. So people may give you the value of holding current just to confuse you, right? But point is, the question is the minimum gate pulse width required to turn on the SCR, which means that you need to look only at the latching current, not at the holding current. Okay. Then the question becomes really simple. So what is the value of the pulse width, or I will call it TP, required to turn on the SCR? So this is a simple circuit. Just apply V is equal to L times di by dt, or I will call this as V is equal to L times IL divided by TP. What is TP? You need to find, right? So TP is L times IL by V. That is 0.1 into IL is what? 100 milli divided by 100 volts. So what do you get as the answer? 100 milli by 100. So 0.1 into 0.1 milli, right? 0.1 millisecond or 100 microsecond. Got it? Any doubts? Simple, right? Just apply V is equal to L di dt. Okay. You will. So this is the minimum value of the gate pulse or the pulse width that you need to give. Okay. To turn on the ACR. One thing you see over here is the pulse width is dependent on the load over here, load and the source, right? So yeah. So 100 for 100 volts and 0.1 Henry. This is the TP value that you need to give. And you also see over here, right? Like SCR has a very large turn on time. The pulse width is actually 100 microseconds. Earlier, we were talking about few nanoseconds as the turn on time, right? But you see, SCRs are having 100 microseconds as the turn on time, which means that you can understand SCR cannot be used for very high frequency applications, right? From this itself, you can understand, correct? Okay. Um, we'll go to the next problem. Same question, just that the circuit is a little different. So I have introduced an R over here, 100 volts, same IL, same IH value. I have a 20 ohm and a 0.1 Henry over here. Okay. So I will ask you to try to remember your circuit concepts. So I guess you have studied earlier in circuits that if you have an RL circuit, right? Then what is the current? So I is actually I naught into 1 minus e power minus T by tau. All of you are aware of this, right? So tau is equal to, okay. So where tau is equal to L by R and your I naught is equal to V by R. Correct? Correct, simple, right? So just apply over here. Your I is actually IL. IL is what? 100 milli is equal to I naught, right? So I naught is V by R. That is 100 divided by 20. V by R into 1 minus e power minus TP. This is what you need to find out, divided by tau. Tau is what? L by R. So what is L by R? L by R is 0.1 by 20 or 1 by 200, right? So 1 by 200. So can we solve this? So 100 milli is equal to 5 times 1 minus e power minus 200 TP. So find out TP. That is the question. Simple, right? I is equal to I naught into 1 minus e power minus t by tau. You know what is I naught? You know what is tau? All the values are given over here, right? And remember that this is during turn on, therefore you need to use IL, right? So 100 milli is your IL, and then you just substitute over here, find out what is TP. Okay. So what is TP? I'll just, if anyone does this faster, you can tell me the answer as well. Okay, so I think you will end up with TP is equal to 1 point, sorry, 0.101 millisecond or 101.01 microsecond. Okay, got this? Can anyone kindly answer, please? If this is okay, or if you are understanding this, even if you didn't get the answer, like if you have not been able to solve the answer, also are you understanding how I did this? This is just an RL circuit. Okay. Or if you want me to pause for 2 minutes or so, I can pause. And then we can go ahead with the next question. Okay. We will go ahead with the next question. Okay. So same circuit. Find the minimum gate pulse width required to turn on the SCR in the following circuit. Just that now I am having a separate R branch and a separate RL branch. So we should be able to do this quickly enough. So again, of course, I forgot to mention your IL values and this. So IL is, take this as 50 milliamperes and IH is, let's say, 25 milliamperes. Always note that IL will be always greater than your IH. That is one more thing, okay? IL is always greater than IH. Okay. So how can you write? If you apply KCL over here, what happens? So what happens over here is, okay. So your IL can be written as this current plus this current, right? So I will write this as I1 plus I2. Okay. So what is I1? I1 is this just an RL branch. So I naught into 1 minus e power minus t by tau plus what is I2? I2 is actually simple V by R, right? So this is V by R. Okay. So what is I naught? I naught is V by R in this branch, right? So V by 20 ohms, correct? Into 1 minus e power minus t by tau plus V by R over here is 5k. This is 5k. Okay. Or V is 100. In our case, V is 100, of course. Okay. So I will write this as 100 by 5k and this is 100 by 20. Okay. So what is tau? Tau is equal to L by R. So L is 0.5, R is 20. So that is 1 by 40. Okay. So 100 by 20 is 5. 5 into 1 minus e power minus 40 t. Okay. Plus 100 by 5k. So what is 100 by 5k? 1 by 50. Right? So 1 by 50 is your IL. What is IL? IL is 50 milliamperes. So find out what is TP. Got it? So it is just a summation of the current. So this current plus this current, I1 plus I2. So I1 is simply an RL branch, right? RL branch, and this is simply an R. So RL branch, for RL branch, I have written I naught into 1 minus e power minus t by tau. And for the R branch, I have just written it as V by R. Okay. So RL branch current can be written as this 100 by 20. I mean, this resistor you need to consider, right? So just find out what is tau. Time constant is L by R. Just substitute over here and then you can get the value of TP. So let's just calculate. 150, 0.02, 50 milli. By 5. Sir. Sir. So you should get something like 0.15 millisecond, or more accurately 150.45 microsecond. Okay. Any doubts over here? This is pretty simple, right? Just summing up the currents and then you just find out what is the value of TP. So you can see over here, right? Like for the same value of the voltage applied and for the same device, you are seeing different values of TP based on the circuit. Okay, and all these TP values are really high, like hundreds of microseconds or tens of microseconds and stuff. Okay, so far we have seen 3 questions, similar questions but different networks of R and L. If you are confident with your networks, you can just easily solve these. These are just LDIDTs, right? Okay. So again, the last question of this type. Next, we will go to the jump on to the next type of question. Okay. So find the value of R in the given circuit if the width of the turn-on pulse is 50 microseconds and the latching current is 40 milliamperes. So everything is given. Find out the value of R. This is a pretty similar question, similar to what we did earlier. Same thing. Just you know that this is the current IL that's getting split into I1 and then I2. So you write IL is I1 plus I2, right? So IL is given as 40 milliamps. 40 milli is I1. So what is I1? I naught into 1 minus e power minus t by tau plus what is I2? V by R. This is the value that we need to find out, right? So 40 milli 0.04. And what is I naught? I naught is V by R. So V by what is R over here? 500 ohms, right? 500 ohms into 1 minus e power minus t is given minus 50 nu divided by. So what is tau? Tau is L by R. So 200 milli is 0.2 divided by 500. Right? 0.2 by 500. So 4 into 10 power minus 4 seconds. Okay. So 4 into 10 power minus 4. Okay. Plus V by R. So what is V? V is 100 by R. This is what we need to find out. And this is also 100. So just rearrange this equation. Simple, right? So 0.04 is equal to 100 by 500 into this expression plus 100 by R. We need to find out what is R. Okay. So just rearrange this expression. We'll be getting 100 by R is equal to 4 minus 1 by 5 is 0.2 times 1 minus e power e power 0.125. Okay. Answer. Answer. So you will be ending up with R is equal to 6060.83 ohms or 6.06 kilo ohms. Okay. These are very simple questions, right? All the values are given. You just need to know during turn on, you need to use your latching current, that is your IL value, and all of these are given. You just need to find out R. Okay. Just apply KCL over here. With your knowledge of networks, you can write what is the inductor current, RL, branch current, R current, and stuff, and then it's just rearranging the terms, right? Okay. So I will pause over here. You take 1 or 2 minutes. You just understand what we have done so far in the past 4 or 5 problems. Then we will go ahead with the next type. Okay. Next question is actually very interesting. So I'll just give you 2 minutes. If you have any doubts or any queries, you can go ahead and ask now. Okay. So still only 2 questions are remaining, and after that we will be done already. Okay. So we'll go ahead with the next question. Okay. This is a pretty interesting question. Find the conduction angle of the diode in degrees. 180 degree, 360 degree, 0 degree, indeterminate. So nothing is given. So no value of Vm, no value of omega. I mean, assume omega as, in general, assume this is a 50 hertz signal, and then you have an inductor. No value of L is given. Just find out the angle in degrees. Okay. A lot of people, what they may do is, okay, you have a diode over here, and this is just a passive load, just an inductive load. So you know that Vm sine omega t is going to be something like this, right? It's 180 and 360 degrees. What people do is generally what you may think also is okay. So positive voltage is still 180 degrees. You know that in half bridge rectifier, your diode is going to conduct for 180 degrees, right? Until it is forward biased. Therefore, people may people may tell, okay, this is the answer, 180 degrees. Okay. However, this is not the answer. This is wrong answer. Okay. You may encounter this question in any competitive exam because this is a place where people think, okay, 2 marks is guaranteed, right? But the trick lies over here, this inductor. We will see what happens. Okay. So I will take a new slide and then it will be easier for me to explain. Okay. 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 So this is your L, this is your V, which is Vm sine omega t. So what is your I through an inductor? I is 1 by L integral VL dt, right? And of course, don't forget that you have a constant of integration, K. Okay, any integration, right? You do an integration, you get a constant. Okay. So this is 1 by L integral VL dt plus K. Okay. So what is I? Just provide me 2 minutes. Okay. So 1 by L integral VL is going to be the same voltage, right? So Vm sine omega t plus K. This is your IL, correct? So first things first, if you integrate this, what do you get? 1 by L. Of course, this constant will appear only after integration. So sorry for that. Okay. So 1 by L, Vm is a constant anyway, and integral sign is minus cos omega t plus K, correct? That is minus Vm by L cos omega t plus K is your IL. So this is your IL, right? So how do you find out K? To find K, use the initial condition. So initially assume that the inductor is uncharged. Therefore, if this is your VL, your I also starts from 0. Your IL starts from 0, but we don't know how it is going to progress, right? But at t equal to 0, IL is 0. At t equal to 0, IL is also 0, right? At t equal to 0, IL is 0. So substitute this over here in the above equation. Therefore, 0 is equal to cos 0 is going to be 1. So minus Vm by, sorry. So if you integrate it, omega will also come here, right? So minus Vm by omega, right? So minus Vm by omega L, and into 1 plus K, which means that K is going to be Vm by omega L. Got it? Therefore, your inductor current is actually minus Vm by omega L cos omega t plus Vm by omega L. Correct? So your IL is Vm by omega L into 1 minus cos omega t. Got it? Till this point, IL is Vm by omega L into 1 minus cos omega t. Okay. Now the only thing that remains is we need to plot this. Okay. So how do you plot at t equal to 0? IL is what? Cos t is 1. So 1 minus 1 is 0. T equal to or omega t, right? So at omega t equal to 180 degrees, IL is how much? So at omega t equal to 180 degrees, this will be minus 1, right? So 1 minus of minus 1 is 2. So 2 Vm by omega L, right? At omega t equal to 90, you will get what? Cos 90 is 0, right? So IL will be Vm by omega L. So what you see is, okay, this is your 90, this is your 180 and so. So at 90, it is Vm by omega L. At 180 degree, it goes to 2 Vm by omega L. So it reaches its peak at 180 degrees. Okay. This is Vm by omega L. This is 2 Vm by omega L. Similarly, during the negative half also, it will be something like this. Got it? So this is your inductor current. Okay. This is your inductor current. So you see the difference, right? You have applied a sinusoidal voltage, but your inductor current is something like this. And it continues like this. Okay. It reaches its peak at 180 degrees. Okay. Here it is Vm by omega L. This is 2 Vm by omega L. Okay. Got it? So the answer to this question is find the conduction angle of the diode in degrees. We saw that the inductor current is something like this. This is 360. This is 180. This is 0. Okay, it reaches its peak at 180, goes to 0 at 360, and again it starts. Okay, so the diode is continuously turned on. Okay, this is the answer. Continuously conducts. Got this question? If you have any doubts, you can stop me and ask me. Okay, just I applied IL is 1 by L integral V dt. And then we applied the constant of integration. We found out its value using the initial boundary conditions. And then we just plotted this. Okay. Simple question, right? So this is actually a rectifier circuit having a pure inductive load. Okay. A pure inductive load. So then what happens is it continuously conducts. Okay. The diode continuously conducts. Got this question? So, okay. So now we can move on to the last question, which is quite similar. Okay. Same thing. This is not a diode. This is an SCR. Find the conduction of the angle of the SCR in degrees. So same sinusoidal source. I have an inductive load. The alpha is 30 degrees. Okay. So what is the answer? 330, 360, 300, 150. Okay. So any doubts you can ask me in the middle also, but I think this will be, I think it should be clear to all of you. Okay. So the point is, you have something like this, right? So this was your input voltage. And we saw that for a diode, it is something like this. This is the conduction. Okay. However, for an SCR, what you will be seeing is, we saw that it starts conducting only after 30 degrees, right? So what you will be seeing is this your IL, this your V. So what you'll be seeing is it will start conducting from 30 degrees and it will stop conducting 30 degrees prior. So 330 degrees. So what you will see is the ACR current will be something like this. Okay, got it. So alpha degree shifted here and alpha degree shifted here, which means that the conducting time, right? The conduction time is not 360, it is 360 minus alpha here and alpha here. So 360 minus 2 alpha. Got it? Got it? So the conduction time is what? Alpha is 30 degrees. So the conduction time is 360 minus 2 into 30, which is 300 degree. Okay. If you want, you can actually verify. You can actually get this waveform using the same method that we did for the diode. Okay. Just that the limits of integration will change. Okay. The limit of integration is right now from only from alpha. Okay. And the initial condition is instead of omega t equal to 0, you can take omega t equal to 30 degrees and you will get the almost pretty much similar expression. But the point is its period of conduction is shifted by alpha. As you can understand, right? It's an HCR after all, right? So it will be shifted by 30 degrees here and it will be shifted by 30 degrees here. Okay. So this is the conduction and the conducting angle is 360 minus 2 alpha. Okay. So I think it is just about time. So we can end the session over here if you don't have any other doubts. So if you have any other doubts, I will open the floor for questions. So far, whatever we have seen today, I mean, if you have any doubts or stuff, you can go ahead and ask.
Yes, but can you explain the last question once again? SCR alpha angle.
Yeah, sure. Just a second. Actually, I'm not going through the entire derivation. I will ask you to do it, the derivation, but the derivation is pretty simple. Just that over here, the initial conditions are going to change, right? Because it's an SCR, correct? So I have given a specific firing angle over here that is 30 degrees. So you cannot conduct until 30 degrees. That is pretty much clear to you, right? So you take the initial time as 30 degrees. That is one. So that will be the lower limit of integration, right? And the upper limit of integration will be 360 minus alpha. Why? Because for every device, for every SCR, there is something known as an extinction angle, right? You may be aware of extinction angle that is called as beta. So I'll just take a new slide and explain. Okay. So for SCRs, so there is this, so starts conducting from alpha. Okay. So this is one and stops conducting at an angle beta. Okay. It's called the extinction angle. Okay. So extinction angle. So generally this extinction angle is the value of this extinction angle will be, okay, I will tell you. Extinction angle will be the conduction time in case of a diode minus alpha. Okay. So whatever is the conduction time in case of a diode minus alpha will be your extinction angle. So we saw in the previous question that the diode was conducting for 360 degrees, right? The diode was conducting for 360 degrees. That means that the extinction angle will be 360 minus alpha. Okay. Same, you take a similar rectifier. Okay. General rectifier also. The beta value will be the conduction time in case of a diode minus alpha. Okay. So this is the extinction angle, which is 2. So from this, if you just see, the total conduction period is just the difference of these two, right? So 360 minus alpha minus alpha. So that is 360 minus 2 alpha. Okay, this is what I used and told that since alpha is 30 degrees, 360 minus 2 alpha turns out to be 300 degrees. You can actually go ahead and find out what is your IL value. You can find out an expression for IL, and that will be a function of alpha and beta. Okay, some cos of alpha and cos of beta terms will come. Okay, I actually wanted you guys to do that. So that's why purposefully I have not included that slide over here. So it will be good if you can derive that expression. Okay, I just solved the example by intuition. Actually, you can tell, right? Because for a diode, you are seeing that it conducts for the entire 360 degrees, right? So if you use an SCR, what might happen? For an SCR, you know that the firing angle is 30 degrees. So for the first 30 degrees, it's not going to conduct. Okay. And for a diode, you saw that it's conducting till 360 degrees, correct? However, you will know that any rectifier, right? Any rectifier circuit, if you have gone through the lectures, you will be having something known as an extinction angle, correct? Any rectifier circuit that does not have a freewheeling diode, okay, that does not have a freewheeling diode, any rectifier circuit, it will have an extinction angle called beta. Okay, that does not have a freewheeling diode. That's the point. So it will have an angle called beta. So you know that it's going to stop conducting some degrees before the normal conduction stops for a diode. Okay, so that angle is again alpha. So alpha during the start is gone, and alpha during, I mean, just before the diode stops, that is also gone. So which means that the diode was if the diode was conducting for 360, then it should conduct for 360 minus 2 alpha. All right. So that's the intuition behind it, and you should be able to tell it as 300 degree. But it will be better if you actually derive the value. Okay, you can actually derive it. I will leave that to you as your home task. Okay, I just wanted to go through these questions, and that's why, yeah. So you got this question right? What was the question?
Yes, sir. I got it.
Okay,
Understood.
it will be good if you
Thank
can
you.
derive the expression, but yeah, like from intuition, you should be able to tell since we solved the diode question that it will be clipped off by alpha degrees on either side. Okay. For the diode question also, there is one more intuition from the options you see. 180, 360, 0 and indeterminate. One thing is, I told this is a pure inductive load, right? Pure inductive load with no freewheeling diode. You know that an inductor current is always, inductor tries to maintain its current somehow, okay? Inductor current somehow tries to maintain its current, okay? It doesn't allow sudden changes in current and stuff. So the answer can never be 0 degree or indeterminate. It's either 180 or 360. Okay. You know that 180 degrees answer for a pure R load. Correct. So these are some ways how you can eliminate other options and arrive at 360 degrees as the answer. But anyway, we saw how it is properly 360 degrees and how we got these waveforms right. Anyway. Yeah. So if there are no more questions, can we end it over here? This session for today? Okay. Okay. So thank you very much, guys, for attending. And yeah, thank you very much. Thank you, Abhinav.
Thank you, sir.
And yeah, thank you, Sudarshan. And good night, everyone. Thanks,
Good
Jeevan.
night, sir.
Yeah, good night, good night. Thanks, Jeevan. Thanks, Pratyush.